Integration is used to find the area of a region, and as it is first defined, it is used to find the area between a curve and the x-axis. But is it possible to find the area between two curves? That is to say, given these functions, f of x in red and g of x in blue, is it possible on the interval from a to b to find the area of the region in between them? And the answer is yes, through actually some simple geometry, some simple arithmetic. To start with, we have the area under the curve of f, which goes all the way down to the axis, to the x-axis. Now that is obviously more than the region we want. But we also have the area bound by the graph of g of x and the x-axis. And that is the region we don't want. So the simple solution here is to find all of the area under f of x, and then subtract from that the area under g of x. So that what we should be left with is simply the area between the two. These two definite integrals can then be combined into a single integral, the integral from a to b of f of x minus g of x dx. Now, this procedure does apply to regions that are below the x-axis or to regions that are straddling the x-axis, partially above and partially below. In the case of a region that is partially above and partially below the x-axis, for example, suppose we have a parabola f of x and a linear function g of x. In this case, the area between f of x and the x-axis would be here, while the area between g of x and the x-axis would be here. Therefore, subtracting the negative area of g of x would add that area on and thus give us the total region that we're looking for. So the subtraction formula, f of x minus g of x, applies even to regions that are below the x-axis because those areas are negative, and when we subtract them, subtracting the negative area actually adds to the area. Now, it is a good idea whenever doing these to sketch the graph, to sketch the region in question, because a very important rule here is that the subtraction needs to be in the order of the function that is greater minus the function that is smaller. In fact, the full definition here of the area of a region between two curves starts with, of course, two functions that are continuous. Continuity is a requirement of integration. So we have two functions that are continuous on an interval from a to b. And let's suppose that f of x is greater than or equal to g of x for all x in the interval. So on this interval, f of x always has a larger y value than g of x, or perhaps equal to, but g of x is never larger. In this case, the area of the region bound by the graphs of the functions on the interval a to b is given by the definite integral from a to b of f of x minus g of x dx. The idea here is that the function that is higher up has to come first in the subtraction. And second in the subtraction has to be the lower or bottom function. The idea is that one of these functions will bound the region at the top and the other will bound it at the bottom, and the order of subtraction does matter. And in order to distinguish that, we're going to need to look at the graphs. For example, let's suppose the region in question is bounded by the graphs of y equals x squared plus 2, y equals negative x, the vertical line x equals 0, and the vertical line x equals 1. This region is easy enough to sketch the graph of. We have a upward facing parabola whose vertex is at 2 on the y-axis. And we have the diagonal line y equals negative x, which is a line that is sloped downward, passing through the origin, with a slope of negative 1. And then we have the vertical line at x equals 0 and the vertical line at x equals 1. Which gives us this region in between. In this region, if we were to partition it in the form of a Riemann sum, the rectangles here would all have the top of the rectangle, that is, would always be bound by the graph of y equals x squared plus 2, where the bottom of the rectangle would always be bound by the line y equals negative x. Thus, the integral here would be from 0, x equals 0 to x equals 1, of the parabola x squared plus 2 minus the line negative x dx. Now again, we could find these two integrals separately, but in many cases it's easier to write them in a single integral like this because we can often combine like terms and create a form that is easier to work with. In this case, this can be rewritten as the integral of x squared plus x plus 2 dx. And this being a polynomial is easy to find the antiderivative of. The antiderivative is x cubed over 3 plus x squared over 2 plus 2x. And again, since this is a definite integral, we can forgo the constant of integration. One cubed is 1. 1 squared is 1. And 2 times 1 is 2. And each of these terms, when x is 0, each of these terms will be 0. So we are left with 1/3 plus 1/2 plus 2, which with a common denominator of 6 would end up giving us 17 over 6. And that is the exact area of this region. Now this can be verified using the calculator, but unfortunately, the calculator is not going to be able to process a region that is bound by two functions such as this. So we will not be able to draw this region on the calculator and have it fill in the appropriate area the same way we would a regular definite integral. The calculator always bounds from below by the x-axis. So we can put the combined integral from 0 to 1 of x squared plus x plus 2 into the calculator and verify that that area comes to be 17 over 6. But when we do that, the region that it draws will not look exactly like the region that we have here. Because instead of treating them as two separate functions and looking at the region between them, the calculator would then be looking at it as a single function, x squared plus x plus 2. So keep in mind that while the calculator can verify this answer, it can only do it with the combined integral, not with the region drawn with the curves as two separate curves. We'll continue on with other examples here. In the previous example, we were given vertical lines that bound the region of integration. But in many cases, it's the functions themselves that determine the limits of integration based on where they intersect. For example, in this case, we're going to find the area of the region bound by the graphs of f of x equals 2 minus x squared and g of x equals x. Once again, we almost have to sketch the region here. We can, of course, use a graphing calculator to look at the region more quickly, perhaps. But we do still need to look at this to know which function is higher up and which function is lower down. In this case, we are looking at a parabola that is shifted up 2, but is upside down. So it will pass from its vertex at 0, 2. It will come down on each side 1 and go out 1. And then it will come down 3 and out 1. So that it would cover a region, it would cover a pattern such as this. We then have the line y equals x, which of course passes through the origin and has a slope of 1. This gives us the region in between Now, we are told that it is an enclosed region. And again, unless we wish to get into improper integrals, our regions will always be fully enclosed. So this is the only region that is completely enclosed by those two graphs. We're not given any other information to enclose a region, so that is what we're looking at. Now, any rectangle drawn in this region, again, if we were to partition in the nature of a Riemann sum, any rectangle drawn in this region would be bound from above by the parabola and bound from below by the linear function. But the limits of integration are going to come from how far to the left can we draw a rectangle and how far to the right can we draw a rectangle. And in this case, visually speaking, it's easy enough to determine those points. The two graphs intersect at -2, -2, and again at 1, 1. These points, or rather the x values of these points, provide the limits of integration, because we can go as far to the left as an x value of -2 and as far to the right as an x value of 1. Now, in this case, we are lucky enough that we can identify the points of intersections of the graphs because they are simple enough graphs. If they were not quite so obvious, we could always determine the points of intersection in the same way that we would do so for a system of equations, by setting both of these equal to each other and solving for the mutual x paired with the mutual y. That solves both formulas. If they both have the same output, then the two expressions are equal to each other. We can move all terms to one side, where we will have x squared plus x minus 2, which factors as x plus 2 times x minus 1, resulting in the x values of -2 and +1. So we can verify from the graph that these are the correct x values to use for the limits of integration. So our limits of integration are from -2 to +1. Our upper function is the parabola 2 minus x squared, and our lower function is the linear function x. And from here, we can easily integrate this. We can simplify the integrand to -x squared minus x plus 2 dx, the antiderivative of which is -x cubed over 3 minus x squared over 2 plus 2x, evaluated at 1 minus the evaluation at -2. Not unlike what we saw in the previous example, we have 1 cubed is 1, so our first term is -1/3, minus 1 squared, which is 1, over 2, plus 2 times 1, which is 2. Now, unfortunately, our lower limit of integration is not quite as friendly as it was in the previous example. So here we have negative 2 cubed over 3 minus negative 2 squared over 2 plus 2 times negative 2. This, unfortunately, will require a little bit more work, but ultimately, we're going to have, from the first set of brackets, we have negative 1/3 minus 1/2 plus 2 minus, in the second bracket, negative 2 cubed is negative 8. But then there is a negative in front of that, which leaves us with 8 over 3. We then have negative 2 squared over 2. Negative 2 squared is positive 4. So we have minus 4 over 2. And then we have plus 2 times negative 2, which gives us negative 4. Now, some of these can be simplified. No, not some, but the 4 over 2 can be simplified to a whole number. But unfortunately, in order to combine with the fractions, they're all going to need to have the same denominator. So rather than simplify the 4 over 2 to a whole number, only to have to turn it back into a fraction, I'm going to leave it as 4 over 2. The common denominator here is 6. So we have negative 2 over 6 instead of negative 1/3, minus 3 over 6 instead of 1/2, plus 12 over 6 instead of 2. Distributing the negative sign will give us negative or minus 16 over 6 instead of 8/3, plus 12 over 6 instead of 4/2, plus 24 over 6 instead of 4. And from here, it's a matter of simply combining the numerators. We have a total of 48 among the positives, minus 21 among the negatives, leaves us with positive 27 over 6, which can be further simplified to 9 over 2. And again, this can be verified using the calculator, although you have to do so with the combined integral, which means the region drawn on the graph on the calculator will not look the same as the region that we drew, because we drew it with the two separate functions, and the calculator will be doing it with the combined function. A couple of further examples. In some cases, it is possible that the graph that is on top and the graph that is on bottom may not be the same all the way throughout the described region. In this case, we will be finding the area of the region bound by f of x is equal to 3x cubed minus x squared minus 10x. And g of x is equal to negative x squared plus 2x. A graphing utility will be very important here. Now we can solve for the intersection points by setting the two functions equal to each other, but that x cubed is going to make things a little bit more difficult. Now, not impossible. There is always the rational zero test along with polynomial division. So even if it doesn't come out to be a nice factorable polynomial, it is still possible that we can factor it using division. But that being said, simply finding the intersection points does not necessarily tell us which function is greater and which is smaller. For that, we would need to graph these. And as it turns out, the cubic graph goes something like this, where the quadratic graph goes something like this. Thus, we have two fully enclosed regions that are separate from each other. Each of these regions is fully enclosed by the graphs of the two functions. The intersection points are not immediately clear, except perhaps at the origin 0, 0. But that is the only one that appears to be quite clear. And even then, we can't be necessarily sure just from a quick sketch of the graph that it actually is at 0, 0. For all we know, it could be very close to it. So if we really want to know for certain the intersection points, we need to take each function and set them equal to each other. But at least now, with the graph in hand, we have some idea of what the intersection points should come out to be. We should see one that is negative, one that is positive, and one that appears to be 0, which certainly does appear to fit this. Moving all terms to one side, the x squareds will cancel out, and we will have 3x cubed minus 12x is equal to 0. And fortunately here, we can factor out a common 3x. And that leaves us with a simple polynomial to work with. Thus resulting in x equals 0, x equals negative 2, and x equals positive 2. The x equals 0 is the x value that separates the two regions. So we have a region that goes from x equals negative 2 to x equals 0, and then a separate region that goes from 0 to 2. And those regions are separate because in the left region, between negative 2 and 0, it is the cubic function that is on top, and the quadratic function that is below. But in the rightmost region, from 0 to 2, it changes. It is now the quadratic function that is on top and the cubic function that is below. So we will need to split this into two separate integrals, one for each region, where for the first region, from negative 2 to 0, it is the cubic function, 3x cubed minus x squared minus 10x, minus the quadratic function, negative x squared plus 2x, dx. And then separately, we have to find the area from 0 to 2, this time with the quadratic function as the upper function, minus the cubic function as the lower function. The good news is that these are the same two functions being subtracted, But since they are being subtracted in the opposite order, they will simply produce the opposite sign result when we combine the terms. The integral from negative 2 to 0 of 3x cubed minus x squared minus 10x, and then when we distribute the negative, we get plus x squared minus 2x dx. This integral will combine to give us 3x cubed. The x squareds cancel out, and the other terms combine to give us negative 12x. Thus, the other integral should produce a simplified integrand of negative 3x cubed plus 12x. Distributing the subtraction into the cubic polynomial will give us minus 3x cubed plus x squared plus 10x dx. And combining those like terms, we have first the negative 3x cubed by itself. The negative x squared and positive x squared cancel out. And then we have positive 2x and positive 10x together giving us positive 12x. So, as you can see here, the two integrals simplify to have opposite integrands. Thus, we now have the area of the region from negative 2 to 0 of 3x cubed minus 12x dx plus the integral from 0 to 2 of negative 3x cubed plus 12x dx. As such, they will also have very similar antiderivatives. 3x to the fourth over 4 minus 12x squared over 2, which will nicely simplify to negative 6x squared. For the other integral, it's the same antiderivative, but with opposite signs. Negative 3x to the fourth over 4 plus 12x squared over 2. So here we have 3 times 0 to the fourth over 4 minus 6 times 0 squared minus 3 times negative 2 to the fourth over 4 minus 6 times negative 2 squared. That's the first integral, according to the fundamental theorem of calculus. Next we have, for the second integral, we have negative 3 times 2 to the fourth over 4 plus 6 times 2 squared minus negative 3 times 0 to the fourth over 4 plus 6 times 0 squared. And while this looks large, keep in mind that this being a polynomial, any power of 0 is 0, and thus each of these will be equal to 0 and will completely drop out. What we are left with then is negative 3 times negative 2 to the fourth, which is 16 over 4 minus 6 times negative 2 squared, which is 4, plus negative 3 times positive 2 to the 4th, which is 16, over 4, plus 6 times 2 squared, which is 4. Some simplification here. (16/4) is 4, times the 3 would give us 12, minus 6 times 4, which is 24. Then we have plus negative 3 times 16/4, plus 6 times 4. And each of these is easy enough to simplify then. And we get a final area of 24. Once again, verifiable using the calculator to find the definite integrals. Understanding, of course, that the region graphed and shaded by the calculator will not look the same as the region that we sketched, because we sketched it with the individual functions, while the calculator would have to show the region of the combined functions. There is one other situation that we should consider here, and that is that some regions might be better done in terms of y than in terms of x. Consider a region bounded by an interesting kind of function. A function that is not a function of x, but instead a function of y. Consider the line y equals x minus 1, which is simply a linear function with a y-intercept of negative 1. But consider then a parabola that has been inverted and might look, therefore, something like this. This region between these two graphs would have an interesting situation to it. More specifically, we would have to treat it as two separate regions, because in the first region, the linear function is bordering the top of the region, while the sideways parabola is bordering the bottom of the region. But on the right side of this, the parabola is bordering both the top and the bottom. So we're looking at a situation where we would have to treat this as two separate regions. Not only that, a sideways parabola is not a function of x. We would have to break this down into actually two separate functions. So we could treat this as something in terms of x, where we would have y equals x minus 1 for the linear function. And then we would have to separate this sideways parabola into one function of x up here, y equals the square root of negative x plus 3, and then a separate function down here, and things can get a little bit messy in order to do this. In order to do this in terms of x, we would need two separate regions. Now, just to make life a little easier here, I'm going to identify the intersection points. As negative 1 comma negative 2 and positive 2 comma positive 1. And of course, this point at this end is 3 comma 0. In this case, we would need two integrals. We would need one from the x value of negative 1 to the x value of positive 2, where the linear function is the upper bound, and the lower part of this sideways parabola would be the lower bound of the region. But then separately, from an x value of 2 to an x value of 3, we would need the blue function, the upper half of this sideways parabola, as our upper function, minus the lower half of the sideways parabola, the red graph, as our lower bound function. And this is not impossible, but it just looks very, very messy. There is an alternative. There is an alternative to this. If instead of having to represent that sideways parabola as two separate functions of x, what if we let x be the output variable and y be the input variable? What if we define it as a function of y rather than a function of x? So the same region with the same diagonal line and the same parabola. Well, I drew that line pretty poorly. Let's see if we can fix that. And the same parabola sideways. But what if, instead of referring to this line as y equals negative x minus 1, or excuse me, positive x minus 1, what if we inverted it to make it a function of y? What if we added 1 to both sides and therefore rewrote this as f of y equals y plus 1? In the same way, we can take the function, the parabola, and instead of writing it as y equals plus or minus the square root of negative x plus 3, what if we squared both sides and then interchanged the x and the y on this equation to give us x on the left, positive x on the left, is equal to negative y squared plus 3 on the right, and therefore called this g of y is equal to negative y squared plus 3. Now, why would we wish to do this? It's the same region, but by doing this in terms of y rather than in terms of x, we get to draw our rectangles sideways. In this case, it's not about a top function and a bottom function. It's about a right function and a left function. To rephrase that, a top function is supposed to have a larger y value, whereas a bottom function has a smaller y value. Since we are interchanging the roles of the variables here, we need the function with the larger x value, the right function, minus the function with the smaller x value, the left function. We also are going to have to watch our limits of integration, because if we're doing this with respect to y, it is y values that we need to look at, not x values. This can be done with a single region from a y value of negative 2 to a y value of positive 1 of the function with the larger x value, the function further to the right, the parabola, minus the function with the smaller x value, the function to the left, the linear function y plus 1. And this looks considerably nicer as a single integral than the two integrals that we had previously. Let's flip back for a moment to see them. These two integrals, which include square roots, which include compositions because they have functions inside the square roots, and therefore would require integration by substitution. If they're simple enough, you might be able to get by without writing the steps of the substitution, but even still, this looks like twice as much work simply for being twice as many integrals. On the other hand, this is a single integral. It does not have any radicals. In fact, it's just polynomial. That looks considerably nicer to integrate. So let's try it. From y equals negative 2 to y equals 1 of negative y squared plus 3 minus y plus 1 dy. Distributing the negative and combining like terms would give us negative y squared minus y plus 2 dy. The antiderivative of which would be negative y cubed over 3 minus y squared over 2 plus 2y from negative 2 to 1. One cubed is, of course, 1 with the negative in front. 1 squared is, of course, 1. And 2 times 1 is 2. Unfortunately, we can't get away with that quite the same with the second limit of integration here. However, not that big of a deal. In this second set of brackets then, negative 2 cubed is negative 8. Then, times the negative in front of it makes it positive 8. Negative 2 squared is positive 4. And 2 times negative 2 is negative 4. This is actually a very familiar integrand and therefore a very familiar antiderivative from a previous example. So, as we saw in the previous example, I'm going to choose not to simplify the 4 over 2 to a whole number. I'm going to choose to leave it as a fraction because I'm going to need to form a common denominator here. Negative 1/3 becomes negative 2/6. Minus 1/2 becomes 3/6. 2 becomes 12/6. In distributing the negative sign here, as well as finding a common denominator, we have negative 16 over 6 plus 12 over 6 plus 24 over 6. And we actually have the same integrand as before with the same result at the end, that this will come out to be positive 27 over 6, which then simplifies to 9 over 2. Now, could we have done this with the two separate integrals with respect to x? Yes, we could have. However, it was relatively little work to convert each of those functions of x into functions of y, and the resulting integral was considerably easier. Now, in upcoming lessons, we will deal with slightly more complicated integrands, and because of the additional complication of them, it might be such that while it is possible to do a region with respect to x, we might find that it is considerably more difficult to do so and considerably easier to do the same region with respect to y. So we need to keep that in the back of our minds as an option, because there are times it is clearly the better option.